Let's explore the different ways of representing data in MATLAB. So far, I've covered creating basic 1- and 2-dimensional arrays in MATLAB, but MATLAB supports much more complicated structures. Creating an array with more than 2 dimensions can't be done directly because there is no simple way to represent 3 or more dimensions of data on a 2-dimensional screen. Instead, you can allocate memory for the array and then define it slice by slice. To allocate memory for the array, I need to tell MATLAB what dimensions to use and what values to put into it. I'll do this by calling the zeros, ones, rand, or randin functions with parameters representing the dimensions of the array. For instance, if I type in zeros, 2, 2, 2, it tells MATLAB to create a 2 by 2 by 2 cubic array where all of the values are 0. Ones creates an array with all values of 1. Rand creates an array where all values are random numbers between 0 and 1. And randin creates an array where all values are normally distributed random numbers. Notice that when I define the array, MATLAB automatically displays it in slices as well. The first 2 dimensions of the array are marked with colons to indicate that they are fully displayed, and then MATLAB displays the slices corresponding to each value in the 3rd dimension. This extends to arbitrarily large dimensions in matrices, although it quickly becomes unwieldy to view the entire matrix on your command window. Now, when you are ready to define the array, you can use exactly the same syntax to refer to each slice. For instance, typing in a of colon, comma, 1 equals bracket 1, 2, semicolon 3, 4 causes the array corresponding to the first z-value of a to take on the indicated values exactly as if it were a 2-dimensional array. The second way you can define more complicated matrices is recursively. MATLAB places no restrictions on what a matrix cell contains, so you can define the cell of a matrix to itself be another matrix. To see how this works, let's quickly define 4 arbitrary matrices. So A equals 1, 2, semicolon 3, 4. B equals 4, 3, semicolon 2, 1. C equals 2, 2. And D equals 3, semicolon 3, semicolon 3. Now, to create a supermatrix that holds each of these matrices as entries, I can define E equals curly brace A, B, semicolon C, D. Be sure to use curly braces here rather than brackets. Now we see that E is a matrix composed of 4 submatrices. We can then access each of these submatrices with curly braces again. So E curly brace 1, 1 returns matrix A, and so on. The last and most general way of holding data is in a data structure. Structures are built-in MATLAB data storage mechanism that allows you to associate multiple pieces of data together. For instance, you might have a list of names and addresses, and you might want to match each name to its address. To create a structure and add data to it, simply define each data field using a dot. In our example, we would say something like s.name equals single quote John Doe, and then s.address equals single quote 123 Fake Street. To add additional data, you can then input data for s of 2, s of 3, etc. For instance, we could say s of 2.name equals single quote Jane Roe, and s of 2.address equals single quote 124 Fake Street. As usual, this is considered a matrix, so your structure can have any number of dimensions and can even contain substructures. Accessing the data works in the same way. Typing in s of 1, 1.name will return just the name of the first data point, while s of 1, 1 with no qualifier will return the entire entry. Inputting s.name with no row or column number will yield all of the names for all fields. With these structures, it is possible to store almost any type of data, no matter how elaborate. Once created, these structures work in a similar manner to a map in Java or C, but they have the advantage of allowing any number of fields for each data point.